Good morning, everyone. Thank you for joining us today. We're here for another deep dive, and today we're tackling something really fundamental. It's all about how we interact with our digital world, input-output systems. Last time we looked at the motherboard, kind of like the system's nervous system. Well, today we're digging into the senses and limbs, you could say. These I/O devices, they're the critical bridge connecting us humans to the digital realm. And joining me to explore all the fascinating bits and pieces of this is our fantastic co-host taking the guest seat today. Welcome.
Hello, everyone. Thank you for having me. It's a great pleasure to be here to discuss this important topic.
Yeah.
Yeah, I'm really looking forward to this, getting into the nitty-gritty of how we actually, talk to our computers. It's essential stuff.
It really is great to have you. So our mission today, for all of you listening, is to give you that shortcut, a way to get really well informed about I/O systems. Doesn't matter if you're deep into tech already, just starting out as a student, or, just curious about how these things work. We're going to pull back the curtain on the theory, look at how key devices actually operate, shine a light on those unsung heroes like I/O controllers. We'll also touch on human-computer interaction, why things are designed the way they are, and wrap up with the connectivity standards that tie it all together. So, to kick things off, let's start right at the beginning. What's the fundamental function of an input device? What's its core job?
That's definitely the place to start. Because, without input, a computer's just a box, right? A powerful calculator, maybe, but totally cut off. At their heart, input devices are what engineers call transducers. Think of them as sophisticated translators. They take our physical actions, pressing a key, moving a mouse, speaking, or things from the analog world, like sound or light, and they convert all that into the computer's native language, the ones and zeros, digital data. They are absolutely the starting point for any interaction we have with a computer. It's how we get our ideas, our data, our commands into the machine.
That translator analogy is perfect, really hammers home how essential they are. Okay, so let's zoom in on maybe the most common input device for many of us, the keyboard. Could you contrast the underlying tech? Membrane versus mechanical keyboards. They feel so different, but what's actually going on inside?
Oh yeah, the difference is huge, and it comes right down to how they're built. Most keyboards out there, the ones that often come with PCs or are cheaper, are membrane keyboards. They're common, usually pretty quiet. When you press a key, you're pushing down on a little soft rubber dome. That dome collapses and pushes a conductive layer on a flexible membrane sheet down onto another membrane layer below it, completing a circuit. That registers the keystroke. The feel is often described as mushy because you're basically squishing rubber. There's not a lot of distinct feedback. It works, it's cost-effective, but maybe not the most satisfying feel. Now, mechanical keyboards, that's a whole different ballgame. It's why gamers, programmers, serious typists often swear by them. Instead of a rubber dome sheet, each key has its own individual mechanical switch underneath, a complex little mechanism. These switches have parts like springs, stems, metal contacts, and there's a huge variety. You hear about Cherry MX switches, right? Blues that click loudly, browns that give you a tactile bump but are quieter, reds that are smooth and linear for speed. Each type has a different feel, sound profile, and requires a specific amount of force to activate the actuation force. So you get much better tactile feedback. You can often feel or even hear the exact point the key registers. It's very precise, very satisfying for many people. Plus, they're generally built tougher, rated for millions of keystrokes. The downsides? Well, they usually cost more, and they can definitely be louder than membrane types. It really shows how a seemingly small tech choice affects the whole user experience, speed, accuracy, comfort, everything.
That precision and feedback difference sounds really significant. And speaking of precision, for pointing and touching in graphical interfaces, the mouse is king, isn't it? How does a modern optical or laser mouse actually detect movement so accurately it feels like magic sometimes?
It's definitely clever tech, much better than those old ball mice we used to have. Basically, it shines a light, either an LED in an optical mouse or a laser beam in a laser mouse, down onto the surface it's on, your desk, a mouse pad, whatever. Then there's a tiny, very high-speed camera sensor inside. It takes thousands of pictures, like micro snapshots, of that surface every single second. These images are fed to a specialized chip called a digital signal processor, a DSP. Its job is to rapidly compare these images, frame by frame. By looking at how the tiny textures on the surface shift between frames, it figures out the direction and the speed the mouse is moving. And then it translates that information into the cursor movement you see on your screen. It's all about rapid-fire image capture and comparison.
Thousands of pictures a second. That's amazing. No wonder they're so smooth now, compared to the old days of cleaning lint out of mouse balls.
Oh yeah, don't remind me.
Okay, so we've covered physical actions like key presses and movement. What about capturing sound? How does a computer take sound waves from a microphone and turn them into digital data?
Right, sound capture. A microphone is another classic transducer. Sound waves in the air hit a diaphragm inside the mic, causing it to vibrate back and forth. These physical vibrations are then converted into a continuously varying electrical signal, an analog signal that mirrors the original sound waves pattern. But like we said, computers need digital, ones and zeros, so that analog electrical signal has to be digitized. This is where the analog to digital converter, the ADC, comes in. It's usually part of your sound card or built into the motherboard's audio circuitry. The ADC's job is to sample the analog waveform. It measures the voltage level, the amplitude of that analog signal, thousands, sometimes tens or hundreds of thousands of times every second. Each measurement, each sample, is then converted into a binary number representing that specific amplitude at that tiny slice of time. String all those binary numbers together, and you get a digital representation of the original sound wave. It's like creating a very detailed dot-to-dot picture of the sound.
That sampling process is key, isn't it? Taking those snapshots to build the digital picture. Okay, so we've fed the computer lots of digital info. How does it talk back? Displays are probably the main way. Let's start with the most common type for years, the LCD. What's the basic principle behind how an LCD display works?
LCDs, yeah, liquid crystal displays, they're everywhere. But the key thing to remember is they don't actually make their own light. Think of them more like incredibly sophisticated light valves or shutters. There's a powerful backlight behind the entire panel these days, usually an array of LEDs shining bright white light. In front of that backlight, you have millions of tiny cells, the pixels, and each pixel is actually made of 3 smaller subpixels, one red, one green, one blue. Now, inside each of these subpixels is a layer of liquid crystal material sandwiched between 2 polarizing filters. The clever part is applying a precise voltage to the liquid crystals. This changes their alignment, sort of twisting them. How much they twist controls exactly how much of that white backlight gets through the polarizing filters for that specific red, green, or blue subpixel. By controlling the brightness of millions of these tiny red, green, and blue subpixels independently, the LCD can mix colors and create the detailed images we see. It's all about controlling light passage.
So manipulating light that's already there, like tiny high-tech blinds almost. But then there's OLED, which seems fundamentally different. How does OLED work, and why does everyone talk about its advantages, especially those perfect blacks?
Yeah, a leaded organic light-emitting diode is a game changer because it throws out that whole backlight concept. That's the absolute core difference. In an OLED display, every single individual pixel is its own tiny light source. It's made of organic compounds that light up when electricity is applied. So if a pixel needs to be black, it just turns off completely. No light emitted at all. That's why you get those perfect blacks and effectively infinite contrast ratios. The difference between the brightest white and the darkest black is immense. It makes colors look incredibly rich and vibrant. Plus, because each pixel controls its own light, they can switch on and off incredibly fast, leading to much faster response times than LCDs. Great for motion clarity in games and movies. And since there's no backlight layer, OLED panels can be made ridiculously thin, even flexible or foldable. Now, they're not perfect. They tend to be more expensive, especially at larger sizes, and there's the potential issue of burn-in. If you display the same static image for too long, it can sometimes leave a faint ghost image. But the visual quality is often stunning.
That ability for each pixel to be its own light source really is the key difference. Okay, moving from seeing images to creating physical copies. Printers. Can you contrast how an inkjet printer works versus a laser printer? Two very common technologies, but totally different approaches.
Absolutely. They both put stuff on paper, but how they do it is worlds apart. An ink printer, as the name suggests, works with liquid ink. It sprays thousands upon thousands of microscopic droplets of this ink directly onto the paper, building up the image line by line. The most common mechanism is often called thermal bubble or bubble jet. Inside the print head, there are tiny nozzles. For each nozzle, a tiny resistor heats a minuscule amount of ink incredibly quickly. This creates a tiny vapor bubble that expands rapidly, forcing a precise droplet of ink out of the nozzle and onto the paper. Then it cools, the bubble collapses, and it's ready for the next drop. It does this thousands of times per second. Laser printers, on the other hand, use a dry process with powdered ink called toner. It's much more complex, actually quite similar to a photocopier. First, a laser beam draws the image onto a rotating photosensitive drum, creating an electrostatic charge pattern on the drum surface. This charge pattern then attracts the toner powder. As the paper rolls past the drum, the toner image is transferred from the drum onto the paper.
Finally, the paper goes through a hot fuser unit, basically, heated rollers, which melts the toner powder and fuses it permanently onto the paper fibers. This whole process makes laser printers generally much faster, especially for text documents, and usually gives them a lower cost per page compared to inkjets. which is why you see them in offices so often.
Two fascinatingly different ways to achieve the same goal. So I've got these input and output devices, but they don't just plug straight into the CPU, do they? There's got to be something managing that traffic. What's the layered communication model that handles the conversation between, say, your word processor and the actual printer hardware?
That's a really important point. No, the CPU doesn't talk directly to peripherals. It would be incredibly inefficient. The whole communication process is managed through several layers of abstraction, using both specialized hardware and software working together. You can picture it as a stack. At the very top, you have the application software, your game, your browser, whatever. It makes a request. The request goes down to the operating system, like Windows, macOS, Linux. The OS provides a standardized way for applications to request I/O operations. The OS then talks to a specific piece of software called the device driver. The device driver translates the OS's general command into instructions that a specific piece of hardware, the I/O controller, can understand. And finally, that I/O controller chip manages the actual electrical signals and data transfer with the physical device itself. The keyboard, the monitor, the hard drive. It's this layered approach that allows everything to work together relatively smoothly, despite the huge variety of hardware out there.
That layered model is crucial for understanding how it all fits together without the CPU getting bogged down. Let's zoom in on two of those middle layers you mentioned, the hardware I/O controller and the software device driver. What are their specific, distinct jobs in making that communication happen? People sometimes mix them up.
Yeah, they're easy to confuse, but they have very different roles, though they work hand in hand. The I/O controller is actual hardware. It's a dedicated chip or a set of chips, usually found on the motherboard as part of the chipset, or sometimes integrated into the peripheral device itself. Its job is to manage the low-level, nitty-gritty details of a specific type of interface or device. So you'll have a USB controller managing all the USB ports, a SATA controller for your disk drives, a network controller, an audio controller, and so on. They handle things like electrical signaling, data buffering, bus protocols, error checking, all the complex physical layer stuff. They basically act as a specialized assistant to the CPU for specific I/O tasks. The device driver, on the other hand, is pure software. It's a critical piece of code that acts as a translator or interpreter. Think of it this way. The operating system knows how to issue generic commands like read data from storage or send this image to the display. But it doesn't know the specific, often proprietary, low-level commands needed to control every single model of hard drive or graphics card from every manufacturer. That would be impossible. That's the driver's job. It's written by the hardware manufacturer, usually, and it translates the OS's generic request into the precise instructions that the specific I/O controller for that device understands. This modularity is key. It lets the OS support new hardware just by installing the right driver without needing to modify the OS itself. It's what gives us such a vast ecosystem of compatible devices.
That separation is so important. The hardware dealing with the physics, the software doing the translation. It makes the whole system flexible. Now, beyond just making things work technically, there's a whole field dedicated to making them work well for us, the humans. What is human-computer interaction, or HCI, and its related field ergonomics?
Absolutely. It's not enough for tech to just function. It has to be usable by people. HCI, human-computer interaction, is exactly that field. It's really interdisciplinary blends, computer science, psychology, design, sociology, all focused on how people interact with computers and technology. The goal is to design interfaces and systems that are effective, efficient, safe, and ideally, even enjoyable for humans to use, making the technology adapt to us, not the other way around. And a really important part of HCI, especially for physical devices, is ergonomics. Ergonomics is more specifically the science of designing things, equipment, workspaces, devices to fit the human body and its cognitive abilities. The aim is to maximize efficiency and productivity while minimizing discomfort, fatigue, and the risk of strain or injury. You see ergonomics everywhere in I/O. Think about keyboard layouts. QWERTY, the standard one, wasn't actually designed for speed, but to prevent old typewriter jams. Alternative layouts like Dvorak claim to be more ergonomic by placing common letters on the home row. Or look at ergonomic keyboards that are split or curved to keep your wrists in a more natural position. Mouse design is huge, two different shapes and sizes. Vertical mice that put your hand in a handshake position to reduce wrist strain. It's all about fitting the tool to the user.
It's fascinating how much science goes into just making a keyboard or mouse comfortable and safe to use for long periods. It really affects productivity. So, digging a bit deeper into HCI, what do we mean by usability, and why is feedback so critical for making a device feel usable?
Usability is a cornerstone concept in HCI. It's basically a measure of how well a user can actually use a product to achieve their goals. It typically breaks down into things like, is it easy to learn? Is it efficient to use once learned? Is it easy to remember how to use? Does it help prevent errors? And is it subjectively satisfying or pleasant to use? A highly usable device feels intuitive. You can often figure it out without needing a manual. It lets you get things done quickly and without frustration. And feedback is absolutely essential for usability. A device needs to clearly communicate back to the user what it's doing or what effect the user's actions have had. Without feedback, you're operating blind. Think about the satisfying click or bump from a mechanical keyboard that's auditory and tactile feedback confirming your key press, the vibration or haptics feedback from a game controller when something happens in the game that makes it more immersive and tells you something occurred. Even simple things, like the little light on your webcam that tells you it's on, that's crucial visual feedback for privacy. Good feedback makes interaction feel responsive and understandable. Things like the scroll wheel on a mouse or multi-touch gestures like pinch to zoom feel intuitive because the visual feedback on screen directly matches your physical action. Clear, timely feedback is key.
That immediate response, knowing your action registered, makes such a difference. It builds confidence in using the device.
Okay, let's talk connections. How do we physically plug all these peripherals in? What's the main standard for wired devices now? And how has its connector design really improved things from an HCI or usability standpoint? Oh, the dominant standard is definitely USB Universal Serial Bus. It's just everywhere, right? Keyboards, mice, printers, drives, phones, almost everything uses it in some form. And the big HCI win in recent years has been the move to the USB-C connector. That small, oval, reversible connector is honestly a usability masterpiece. Remember the old USB-A plugs? The frustration of trying to plug it in, getting it wrong, flipping it over, still getting it wrong somehow, then flipping it back and it magically works. USB-C completely eliminates that. It plugs in either way. It sounds like a small thing, but removing that tiny point of friction hundreds or thousands of times over the life of a device, that's a huge usability improvement. A fantastic example of designing for the human user.
Yes, the end of the USB superposition state where it's simultaneously both the right way up and the wrong way up until observed. USB-C is a relief. But for even more demanding tasks, there's another interface often using that same USB-C connector, right? What is Thunderbolt and what's its main advantage?
All right, Thunderbolt. It's a high-performance interface initially developed by Intel and Apple that also uses the USB-C physical port. What makes it special is that it essentially tunnels other high-speed data protocols directly over that USB-C connection. Specifically, it carries PCI Express, PCIe data, the same fast connection used inside your computer for graphics cards and NVMe, SSCs, and DisplayPort video signals. Its primary advantage, the big headline feature, is simply bandwidth, massive bandwidth. Current versions like Thunderbolt 4 offer 40 gigabits per second bidirectionally. Thunderbolt 5 is pushing even higher. This makes it perfect for things that need huge data throughput. Think connecting super fast external SSDs, daisy-chaining multiple high-resolution monitors like two 4K displays or even an 8K display, or using powerful docking stations that connect your laptop to a whole desktop set up monitors, network peripherals, all through a single cable. It consolidates high performance into one port.
That single cable solution for high-end setups is incredibly appealing. Okay, we've covered a lot of ground, from basic input to high-speed connectivity. To wrap it all up, how do all these different components, the devices, the controllers, the drivers, the design principles come together to create that functional bridge between us and our computers?
Well, pulling it all together, this whole I/O system is what makes computers useful tools for humans, rather than just abstract calculating machines. We started with input devices, keyboards, mice, microphones. They act as our translators, converting our intentions in the analog world into the digital language the computer speaks. Then you have the output devices, monitors, printers, speakers doing the reverse translation, taking the computer's digital results and presenting them back to us in ways we can see, hear, or touch. And crucially, this conversation isn't direct. It's orchestrated by that vital partnership. The hardware I/O controllers managing the physical nuts and bolts, the electrical signals, the data flow. And the software device drivers acting as the specific interpreters, translating between the OS's general commands and the hardware's unique language. Importantly, the design of all this isn't just technical. It's deeply informed by human-computer interaction principles. We need devices that are not only functional, but also comfortable, ergonomics, and easy and effective to use, usability, providing clear feedback. And finally, standardized connectivity methods like USB, Thunderbolt, and wireless ones like Bluetooth and Wi-Fi provide the common ground, the universal plugs and protocols, allowing this huge, diverse ecosystem of peripherals to connect and communicate reliably. It's this entire interconnected system, hardware, software, design principles, standards that forms the bridge, transforming the raw processing power of the computer into something we can actually interact with and leverage in our daily lives.
That's a perfect synthesis. It really underscores how many layers and considerations go into something we often take for granted, just plugging something in and having it work. It's the seamless integration of all those parts that makes modern computing possible. From the feel of the keys under your fingers to the pixels on your screen, I/O is constantly mediating that human-machine boundary. So as we wrap up this particular deep dive, I want to invite everyone back for our next series. We'll be exploring system stability, power, cooling, and thermal management. Equally crucial stuff for keeping our machines running smoothly. And just a final thought to leave you with today. Think about how I/O is evolving. It's not just simple input and output anymore. We're seeing more complex interfaces, things that augment our senses, brain-computer interfaces on the horizon. It's pushing the boundary of what interfacing even means. Where do you think the next major leap in how we interact with our machines will come from? Something to ponder. Thank you all for joining us on this deep dive. Don't forget to subscribe to Tech AI and Beyond for more insights into the fascinating world of technology.